All right, we're after 4. So we got 3 talks today. Thanks everyone for joining. Each of them 30 minutes long. But before they start, I'm going to pass it over to Julie McHenry just to kick things off.
Okay, great. Thanks everyone for being here. So I'd like to open first by thanking each of the 3 individual survey committees for having done such a good job over the past month, processing a huge amount of community input and writing 3 really excellent reports. This process has been everything that I hoped it would be, and they had a huge role to play. I also want to thank everyone who's engaged with the process in any way at all, whether it's writing white papers or science pitches or participating in meetings. These surveys that you will hear described today are the culmination of the sort of processing of all of the input from a large number of people. And the surveys are as good as the input, and the input was fantastic. And then I wanted to remind you that these are not the actual final surveys. It's an intermediate product. We're making it available now because you can use what's in these reports to get a pretty good idea of where thinking is going on the surveys. The final as defined surveys will likely be the same or quite similar to what's described in these reports. But we are still working on aspects of feasibility and scheduling. And of course, our top level committee, the Roman Observations Time Allocation Committee, thank you to all of you, will be considering all 3 surveys as an ensemble and making a final recommendation on an overall observing plan. So with that, I will not take up more of the time of this meeting, and look forward to hearing what the 3 committees have to report. Thank you.
Okay, so I guess I'm good to go, Tom?
Yeah, go ahead, Dan.
Okay. Okay. Thanks everybody. Thanks Tom and Julie for the introduction, and thanks everybody for joining. It's a pleasure to give a brief summary today of the report on the Galactic Bulge Time Domain Survey Definition Committee. So I'm giving this report a summary, of course, on behalf of a large group of people on the definition committee, which I've co-chaired with Jesse Christensen, who's on the line, I think, over the last year. So the report, as you will see, which is now public, is fairly long. It's something like 60 pages, a bit over 60 pages. So in the 20 minutes that I have here, I will try to give sort of course, a high-level summary of the main recommendations. So for those of you who don't want to read the whole 60 pages, this will hopefully be enough to process what the main recommendations are. But of course, a lot more details are in the report itself, and I won't be able to go into all those details. But of course, we're happy to answer the questions that come up in the forum after the talk and also offline afterwards. Okay, so to get started, just a brief introduction to the committee. So our committee consisted of 12 community members across a wide range of expertise, all the way from solar systems to exoplanets to stellar astrophysics, galactic astronomy, and extragalactic astronomy. I also want to highlight the contributions from additional contributors, all of them early career researchers who've helped committee members with various aspects that were important for making the recommendations that are in the report. So just as a brief reminder, I guess, as an introduction to put everyone on the same page, the scientific goal of the Core Community Survey for the Galactic Bulge Time Domain Survey is to carry out a census of exoplanets in the galactic bulge using the gravitational microlensing method. The main advance here will be to probe a parameter regime in planet mass and same major axis that is distinctly different from the exoplanet census that we currently have. So Roman will probe in particular low mass planets at large orbital periods, at large same major axis, which were not accessible using, for example, transit surveys such as Kepler, which is shown in red. So the main goal to do this, and in order to do this, we need to obtain time domain, time series photometry of a large number of stars in a large field towards the galactic bulge, because you need a high density of stars in order to get sufficient number of lensing events in order to perform the statistics and build up the statistics in order to perform the census of exoplanets in various parameter spaces. So I'll start off with sort of talking a little bit about what I call here the reference survey, which is one version of how the galactic bulge time domain survey might look like, and a version that has been proposed or described prior to the definition process. And the reference survey I'll use here, just to again put everyone on the same page, is the one from Matthew Penny's 2019 paper. So basically, right, one reference survey that the way that the survey can look like is that you have fields within the galactic bulge. So one of these rectangles is one footprint of the Roman WFI instrument. And you observe a certain number of these fields consecutively. So Roman observes one of these fields and then steps over to the next one, to the next one, to the next one. And once it's done, it repeats the same the observing pattern and builds up a time series and light curves of stars that are in those fields. So in this particular case, we have 7 fields. So these are 7 fields that are observed in each season. The galactic bulge is observable in seasons. There are 10 seasons in the total 5-year Roman missions. So in this reference survey, Roman would observe the galactic bulge as part of the galactic bulge time domain survey, these fields 6 times. And the galactic bulge is observable for 72 days. So there will be 6 times 72-day observations following this pattern. And that builds up the survey, which has a total duration of 420 days. So this is the nomenclature that we're using throughout the report, which is sort of important to keep in mind, right? The survey is the total duration that will be allocated to the galactic bulge time domain survey. The seasons are the times when Roman is observing the bulge and when the bulge is actually observable. And the fields are the locations of the fields within the galactic bulge that will be observed. The cadence that will be built up, nominally in the reference survey is 15 minutes with a broadband filter. So that's basically how long it takes to slew around the whole field. And there will be additional narrow filter observations with a slower cadence in this reference survey. That cadence was about 12 hours. These additional narrow filter observations are important for the mass measurements that come out of the macrolens for the exoplanets that are discovered using the macrolensing method. So the green box here in the bottom shows you some ideas of sort of changes that you can make to this sort of nominal reference survey while still fulfilling the level 1 science requirements with respect to the exoplanet census that Roman will discover. So you can, of course, change the survey duration. That's actually given by the Roman project that will define what we call the nominal, underguide, and overguide survey. You can change the amount of time that you spend observing each season. So the maximum is 72 days. That's due to spacecraft restrictions, pointing restrictions, but you can, of course, decrease this number. You can also, of course, change the number of fields that are observed in each season. That's 7 here, but you can change this something from between 5 and 9 fields. And that will, of course, then also affect the cadence, which can vary and can be shorter than 15 days, but it cannot be slower. And you can, of course, also change the cadence of the narrow filter observations. So the input that we've used for our deliberations, and many of you have seen this probably before, came, of course, from you, from the community. So our committee received something like 20 white paper submissions and 40 science pitches. These are word clouds just to illustrate the breadth of science that has been suggested, in addition, of course, to the exoplanet microlensing science that will come out. So there's a huge amount of science that can be done using time domain photometry of fields in the galactic bulge, and our job and our mission was really to recommend what we think is the best possible survey in terms of diversity of science while still fulfilling the level 1 requirements. So we've reviewed the submissions that we've received from the community. We did this using metrics. I won't go through this in detail because it's a fairly detailed table, but basically we reviewed them in terms of impact. So how impactful is the science that has been proposed that can be done? How feasible is it while still achieving the level 1 requirements? Of course, Roman needs to detect exoplanets using microlensing, and so we can't do changes that are too drastic and that will decrease the yields. And then there are a couple of other metrics in terms of synergies. So is there synergy with other science cases? Are there synergies with surveys, for example, ground-based surveys or other space-based surveys that are operational, and how unique is the science case with respect to what Roman can do compared to other instruments. So we've reviewed and ranked these submissions over something like a month period, and then identified from the submissions common science themes. So we didn't necessarily pick individual white papers, but we grouped them into science themes. And then through interactions with the community at various points last year, which are listed here, we sort of had an iterative process where we came to prioritize some science themes over others. So one of the considerations that all of us and all the committees have to deal with are, of course, what we call trade spaces. So they're trade-offs. We cannot implement everything, because if you implement something, then something else has to give. And the key trade space, just to illustrate the sort of considerations that we have to go through, are for the galactic bulge time domain survey are the exposure time, the number of fields, and the cadence. So once you fix two of these numbers, the third one is set, right? So you can only basically specify the exposure time and the number of fields. That sets the cadence, and you can play this game with other two variables as well. The cadence does have a firm requirement that it has to be faster than 15 minutes. So the way that we made our decisions is that basically there were a very broad slew of simulations that were run by a team led by Matthew Penny, using the latest galactic population synthesis models and the latest slew and settle times of the spacecraft to simulate the exoplanet yields from microlensing. And those simulations produced yields based on a fiducial mass function of what we believe the mass function currently looks like, and then optimized the field layouts based on the yields themselves. And so basically that gave the committee a menu of options with different parameters, such as exposure time, number of fields, and cadence, that we then considered and voted on. Just to give you an idea of the trade-off of what this looks like, on the right-hand side here is a graph showing the cadence that results from a given simulation as a function of exposure time and as a function of the number of fields, as is shown in the numbers here. And the colors are the yields of exoplanets discovered using microlensing. In this particular case, is a 1 Earth mass free-floating planets. So you can see the trade-off clearly, right? So if you increase the number of fields, then the cadence will increase. If you fix the number of fields and you increase the exposure time, the cadence will increase, and the yields, the exoplanet yields, would also increase because you're increasing the exposure time, and so on and so forth. So you basically have trade-offs here that you have to consider in terms of how many numbers of fields do you pick, what is the resulting cadence, and how does that impact the exoplanet yield. So let's move on now to the recommendations. So I'll go through these fairly quickly to have enough time to basically talk about the main survey recommendations. But the individual recommendations are first in terms of what we call the high cadence fields will look like. So those are the nominal fields where we get basically better than 15-minute cadence in the galactic bulge. These are recommendations that basically follow the reference survey. We recommend that there will be 6 high cadence seasons, and they should be the first 3 and the last 3 bulge seasons. Remember, there are 10 seasons in total, so we recommend that the first 3 and the last 3 are used for high cadence observations for microlensing. And that is important because you want to build up a baseline for astrometry to basically measure proper motions of the source and the lens. And that helps with mass measurements, for example. We also recommend that the fields will be placed in the southern galactic bulge, not the northern galactic bulge. This is because of extinction, which is larger in the northern galactic bulge, and because of a longer history of ground-based observations. Again, these are recommendations that are in line with what the reference survey previously had assumed. Recommendation 2 is a significant change, and that is that we recommend to add a field in the galactic center. So there's a huge amount of science that would be enabled by this. 2 examples are shown here. So on the left is an image showing the Chandra X-ray sources. A lot of the X-ray sources that have been detected are in the galactic center. So by placing a Roman field in the galactic center, we get time domain infrared photometry for these sources. On the right-hand side is a graph showing the stellar populations that will be probed in the galactic center. So there are very interesting populations in the galactic center, nucleus star cluster, the nucleus stellar disk, various clusters that will all be probed. So this is a density as a function of distance from the galactic center. That will all be probed by a single pointing with Roman, right? So a single pointing of Roman covers a wide range of these stellar populations, for which we can then get kinematics, time domain photometry, to probe things like compact object binaries, variable stars, transiting exoplanets, accretion onto Sagittarius A star, and so on and so forth. Many of those science cases very strongly also benefit from having the same cadence, the high cadence that the microlensing fields, the regular microlensing fields will have, variable stars, exoplanets, and so on and so forth. Recommendation number 3 is that we advocate to maximize the season duration and the cadence. So maximizing season duration, we mean that you have a maximum of 72 days, but if the allocation in the season is less than 72 days, we still want the baseline. So even if you only observe 65 days, we want the first observations and the last observations to span that full duration of 72 days. The cadence, that is again mostly helpful actually for the exoplanet microlensing mass measurements. The cadence increase is important for many other science cases as well. So I'm showing 2 here. One is the transiting exoplanet science case. So this is by a white paper by Robbie Wilson showing that the relative change in planet yield is a function of cadence. And you see that especially for small planets, sub-Neptune-sized planets, you do a significantly better job of recovering these the faster you sample. Astroseismology of red giants also very strongly benefits from a faster cadence. So these are yield calculations of oscillating red giants in the galactic bulge, showing that if you have a 50-minute cadence and a 7.5-minute cadence, so twice the cadence, you basically double the amount of detections that you have, in particular for the very numerous red clump stars, which are very important for probing populations in the bulge. There are also benefits for microlensing. I've mentioned some of them. Another one has been pointed out by a white paper by Andy Gould, which is that faster cadence improves the detection of low-mass free-floating planets. Okay, another recommendation that we make is that we should maximize the cadence of the colors that are obtained. So these are the narrow filter observations. There's a requirement to have 2 of these observations, one in a blue filter, one in a red filter. But the cadence themselves is basically up to us to recommend and to specify. So we recommend 2 filter cadences with 6-hour cadence spaced by 3 hours. So you basically get 1 extra narrowband filter every 3 hours. We do make a recommendation as to which filter those should be, but we actually punt the definitive decision of what those filters should be to the project infrastructure teams that are looking into optimizing that choice. Because it's not immediately clear yet for the microlensing yield which filters are the best. So we sort of punt this decision, but we do make a recommendation that the cadence should be faster than 12 hours, which was the number used in the reference survey. Another substantial recommendation that we make that is quite different from the reference survey is that we advocate for adding what we call low cadence seasons. So remember that there are 10 seasons nominally within the 5 years. The first 3 will be high cadence seasons for microlensing. And so that leaves an additional 4 seasons in the middle. And we advocate and recommend that we should obtain observations with lower cadence in these seasons where no high cadence observations will be obtained. This is very important for capturing microlensing events of more massive objects, in particular isolated black holes. The duration of the lensing events increases very strongly with the mass. So you can see this in this example here. So, if you have a lensing event that looks like this, you would totally miss it if you don't do low cadence observations. You don't need the high cadence for these lensing events. So low cadence observations are just fine. We did some work led by Jessica Liu on actually optimizing the cadence. So how often do you actually have to go back in these off seasons to obtain these observations? And we converged on a cadence that's basically, if you do better than 5-day cadence in these off seasons, you have a substantial improvement in the mass precision that you can recover for these isolated black hole microlensing events. So in this particular case, you get a 3 times mass improvement for over 1,000 events if your cadence is faster than 5 days. Now, the last 2 recommendations are what we call snapshot observations. So those are observations that are only done at a very, very, I wouldn't even call it cadence, every once in a while, basically during the galactic bulge time domain survey. One of them is to perform what we call snapshot photometry. So Roman, the wide field instrument, has many filters. 2 of them, one of them is used, the broad filter, for the high cadence observations. 2 are used for the color cadences, but it still leaves an additional 5 filters where we don't get any observations. So what we recommend is that you observe all fields in the remaining 5 filters that are not obtained otherwise with a given signal to noise in order to just basically get additional filter information of all the stars that are covered in those fields. So you can see that the filters, of course, they cover different parts of the SED of different types of temperatures of stars. But if you have M dwarfs, for example, then having additional colors will really help with basic stellar characterization of the fields that we're obtaining. This is fairly cheap. This is about 5 hours per snapshot. So these are really cheap observations that we think really multiply the science that we can do in a fairly cheap way. Now, finally, the last recommendation, which is something that came out of discussions within the committee, is to also perform snapshot spectroscopy. So the Wide Field instrument has a GRISM instrument that can do low resolution or 500 spectroscopy. This will be challenging because the fields will be, of course, quite crowded. So this is an example of a simulated field using slitless GRISM spectroscopy in the field. And you can see there's lots of spectra that are overlapping because you have lots of stars. So this will be challenging in terms of sort of a data analysis perspective, but we're fairly optimistic based on work led by Hans-Walter Rix and collaborators that we can actually really recover important parameters from these spectra, temperatures, of course, metallicities of the stars, radial velocities that we would otherwise not get. And that would be a huge science multiplier if we can recover this from the spectra for the stars that are observed as part of the galactic bulge time domain survey. Again, this is fairly cheap, about 3 hours per snapshot, covering all the fields. Okay, so a couple more slides. So unfortunately, of course, we couldn't recommend everything that was suggested by the community. There were lots of great ideas, many of which we talk about in the report, and we specifically say that would be great to implement as part of general astrophysics survey within Roman. I'm covering a couple here. So there were several white papers that suggested to observe a globular cluster. There's huge amounts of science that can be done. Unfortunately, as you see in this graph here that shows globular clusters with respect to the field choices, most of them are quite far away from the nominal fields, and so the slew times would be prohibitively expensive. The same is true for the Earth transit zone, which is a region in the galactic plane where other stars can see the Earth transit, and similar considerations were made for the suggestion of obtaining very high cadence observations, so a cadence of something like 1 minute or so. Okay, so this is the last slide because I know I'm running out of time. So this is basically the big summary of what the recommendations are in terms of the 3 different survey durations that we were given, the nominal, the underguide, and the overguide. So in the nominal survey, we have 420 days in total. So we recommend the field layouts as shown here, 6 high cadence seasons with a duration that's a bit shorter than the maximum because it needs to fit into 420 days. We recommend 6 fields to be observed with a 15-minute cadence. Those are the 6 fields down here at the bottom. We also advocate for adding the galactic center with the same cadence. So basically, you now have 7 fields, and the resulting cadence will be 15 minutes. We advocate for 4 low cadence seasons with a cadence of 5 days. And we recommend to obtain photometric and GRISM snapshots, 12 in total, 2 for each high cadence season, 1 at the beginning and 1 at the end. This implements all the science components while optimizing the science requirements. So that is, it will yield microlensing exoplanet detections that should allow, assuming a fiducial mass function, to achieve the level 1 science requirements. The underguide compromises on this on the lower survey duration by decreasing the duration of the high cadence seasons, only 63 days. And in order to make the microlensing exoplanet yield still feasible for the level 1 requirements, we now remove the requirement of having the galactic center observed at high cadence. So the galactic center will still be observed, but at a much slower cadence. That increases the cadence for the remaining fields, for which we now have 7. So there are 7 sort of microlensing fields that have a cadence of 12 minutes, and we have a minimal amount of photometric and GRISM snapshots. So this really enables some minimal amount of extra science while still meeting those science requirements. And then finally, the overguide, of course, implements more than that. In particular, it increases the total season duration. We decrease the number of microlensing fields in order to obtain a higher cadence. So now we have the microlensing fields plus the galactic center at a 12-minute cadence. So that improves, things I've talked about before, transit exoplanet science case, as well as the astroseismology. we have low cadence observations with an even faster cadence, 3 days, and we have a larger number of photometric and GRISM snapshots. So this really maximizes the extra science, in particular the cadence increase, while still meeting the science requirements for exoplanet microlensing. Okay, and I've already gone over, so I'll stop here. Thanks.
Yeah, thanks, Dan. That was great, and we thank the work of your committee. We have several minutes now for questions. So either put your question in the chat, raise your hand, unmute. Okay, I see Robbie Wilson has his hand up. Go ahead, Robbie.
Hey, Dan, this is great work. Thanks for the committee, first of all, for everything. My first question, maybe this might be a Matthew Penny question, but I'm curious what changed to make the field layout different from that nominal 7 design? Like, is it a different galactic model or yield estimates, or what motivated that?
I'll try to give my best representation of Matthew Penny if he's not online, but he might be. I think so. One of the changes that were made was definitely the galactic population model. I believe that has changed significantly from the 2019 work, which in turn affects the extinction and other considerations that I think my sense is that this is the largest change in where exactly the fields will be placed. But it's all driven by optimizing the exoplanet yield, basically.
Yes, I believe there was also updated extinction and dust maps that were part of it.
Okay.
Yes, that's true, especially for the galactic bulge and galactic center region.
Thanks, Jennifer.
Okay, thanks.
Okay, we have time for more questions. We're not going to start. Scott Gowdy, great. I was going to say we won't start the next section until at least 4:30 because I tell people that join in late for the surveys they want to hear. So Scott, go ahead.
So I'm particularly struck by the decision to go to 5 fields in the overguide. I recognize this decreases the cadence and that improves the yield for low mass or small planets in terms of microlensing transits, but it also increases the yield of those, but it decreases the yield of large planets overall, just because you're not signal to noise limited, you're just limited by the number of target stars that you look at. And that brings, a different kind of science, right? In particular, you're sensitive to very rare events that are high signal to noise, but very rare in terms of both transits and microlensing. And I won't try to speak intelligently about the other science. So what was the motivation for that?
Yeah, I mean, it was really mostly, I mean, I guess Matt will again be the best person to answer that question, but it's mostly driven by decreasing the cadence to allow to maximize other science, while still, I mean, based on the simulations, the yields, right, for example, for both the free-floating planets and the bound yields in the various mass ranges would still, according to the simulations, not differ that dramatically from, for example, the 6-field layout in the nominal mission. And my sense from this is that you gain a little bit by having longer seasons, and you gain a little bit by decreasing the cadence. I mean, you're right that it presumably, there's some trade-off in terms of the parameter space of the planets that will actually get boosted, and some of them will decrease in terms of the yields. But the yields themselves, right? So this is in table 11 in the report. Don't change that much if you go to a layout where you only have 5 fields instead of 6. Not to the point where it seemed to us on the committee that it would jeopardize the level 1 requirements, assuming the mass function, the fiducial mass function that was put into the simulations.
Okay, thanks.
But in terms of, I guess to answer your question, in terms of this, the scientific driver was really the fact that we had some, strong input from the community, and also generally, also in the exoplanet microlensing case, the free-floating low mass planets, that increasing the cadence, going faster, would be really valuable. So that was the main driver.
Thanks for the question, and also thanks, Sean Terry. You just posted the link to the reports, which were put online a few hours ago in the chat. I meant to do that, but thanks for doing that. We've got time for let's say one more question if there are anything else. That I think Sean's asking a question.
Yeah, just one quick one. Thanks again, Dan, and the committee for all the work. So just an idea of moving forward. Now the ROTAC has these in their hands. You mentioned near the beginning of this. So of course the ROTAC is charged with several things to do, but one of them for the GBTDS is to define exactly the lower cadence filter selection. So that you said punted to them, plus maybe coordination with other pit teams. Is that generally what we expect to happen?
Yeah, so this is one. I mean, I don't think there's any other knobs that we didn't necessarily specify or recommend where we punted the decision. But the one the filters, so which filters to use for the color cadence, so the 3 hour or 6 hour cadence, the specific filters, that is something that I mean maybe Scott or others from the pit can comment on this, but it hasn't really been optimized. It's not going to make a huge difference in terms of the total survey time. Of course, the filters, right, depending on which filter you choose, the exposure times will be slightly different. But the fact that we didn't recommend this specifically or say you need to use those filters reflects the fact that this hasn't been optimized yet, and it's also not a decision that really needs to be made right now, because even at the ROTAC level, it won't matter that much because of the fact that it's a lower cadence and it's the total survey duration that basically matters most.
Okay, thanks. So by the time the ROTAC delivers their final, makes their final decisions, it will be decided. Is the expectation?
That is
March, April, whatever the timeline is. Okay, got it.
Yeah, March. So that is the expectation. So it's spelled out in the preamble of the report that was just posted. So the expectation is that the ROTAC will recommend something by March.
Okay.
And my understanding is that by then the filter choices will also be set. Yeah.
Thanks.
But others can chime in if that's on record.
Yeah, actually, I asked this to Julie and Jeff at the AAS meeting, and Jeff made the point that the final decisions on filters will be made after commissioning. If there's some issue with a filter, then it might, they might be changed. And we have more work to do in August pit to try and optimize the choice. But the current choice looks like a good one at the moment.
Okay, I think we'll leave it there on this survey. Scott's got his. Scott, did you want to say something real quick? Or
Oh, I actually meant to do the applause thing. I just wanted to say thanks to the committee for doing all this hard work. I know it was a lot of work under a very short amount of time. So the report looks great. Thank you.
Yep, thanks very much. All right, we should move on now to the next survey, which is the high latitude time domain survey. I think. I
think we were wide area survey next.
All right, then it's the wide area survey.
Whatever was on the calendar.
I see you appeared, Ryan. So I'm sure you're right.
I hope so. I thought that was what it said. Hi everybody. Let me try to share screen here. Share this screen. Share slideshow. Does everybody see that? Okay.
Yeah, that looks great. Take it away.
Wonderful. Okay. Hi everyone, I'm Ryan Hickox from Dartmouth College. I'm one of the co-chairs of the High Latitude Wide Area Survey Definition Committee, and I'll give you again a quick sort of 20-minute rundown about what our recommendations are. So just in terms of the members of the committee, here's a group of people here. They have a wide range of expertise and backgrounds. Risa Wechsler from Stanford is the co-chair, and we also were we had a lot of people on the committee proper, and then also some wonderful support from our solar system liaisons who are on the right here. Okay, so outline of what I'll tell you today, I'll just give you an overview of the survey, give a quick introduction to what the in-guide recommendations are. Then I'll go through the committee process, talk about how we did the various trades, things we decided not to do, what our overguides and underguides are, and then finally what one could do in the future with survey extensions. So I think you've probably already seen this in the last talk about what the core community surveys are. So we are the widest area survey. We're also the one that takes the largest amounts of nights. And the idea is to do multi-band imaging and slitless spectroscopy over a very wide area. And so here's the lots of bullet points introduction slide. I'm not going to go through all this, but I figured I'd leave stuff up here for reference if anyone looks at the slides later. The idea behind the survey is to do both imaging over a wide area. The prime driver from the cosmology side, in terms of the cosmology requirements for Roman, for the imaging is weak lensing for cosmology, taking advantage of both depth and also angular resolution and well understood PSF and the near IR coverage that we get. And then spectroscopy also contributes to the cosmology goals via galaxy redshift survey in two ways, by looking at baryon acoustic oscillations and redshift space distortions. And then finally, and this is important, there's also an overall mission objective for a wide field infrared survey with imaging and spectroscopy to greater than 26.5 mag. And so this survey meets that goal, and it's enormously powerful for a very wide range of sciences that hopefully I can only begin to touch on, but hopefully you'll be able to see. And in terms of our observing time, our in-guide allocation is 520 days with 20 above and 40 below. And I'll describe what we recommend for that as we go on. Okay, so this is the main architecture. This is like the summary slide for what we have recommended. Is ultimately come down to a survey with 3 tiers. The medium tier looks a lot like what the design reference mission survey that was put together for Roman does. It's 2,400 square degrees, including 3 imaging bands, Y, J, and H band, and then GRISM spectroscopy over this whole area. And so this is designed to do the weak lensing measurements, to provide this wide area survey, and then also allow for detailed cross calibration and for the weak lensing measurements, which we get from the multiple bands, and also a very wide range of astrophysical applications. The wide survey then goes even wider than this, so more than doubles the area. And this is now done in a single band, which is the one that's most sensitive for the lensing. So it allows us a bigger area to do lensing, but also has a lot of applications for cosmology and general astrophysics. And I think a really key point here is why we ended up on also this very wide single band tier was that it was advocated for in a substantial numbers of white papers, science pitches, and community inputs. We had a number of folks wanting to survey the entire LSST area or even the entire sky, which we didn't get to for reasons that I'll describe later on, but this is moving in that direction and I think achieves at least some of those science goals. And then lastly, we were always going to need a really deep calibration tier that's essential for the cosmology, both for the imaging and spectroscopy, but this is also, so this is a 5 square degree region, and this with, sorry, excuse me, this is up to a total of 20 square degrees, but with this 5 square degree region with ultra deep imaging. And this is also useful for not only that calibration, but a very wide range of astrophysics. And so in terms of the recommended field placement, we have these big patches of sky here. The suggestion is that the things that came into this were both, well, I'll mention a little bit what the considerations were, but basically the recommendation that went into our report was a medium tier that covers both part of the north and south galactic cap, and then wide tier that covers a wide area of that as well. And we had a bunch of considerations that I'll describe later. The deep calibration fields are LSST deep drilling fields, and those are also inside these medium tier footprints. Okay, so in terms of what the numbers look like, again, it's, well, I don't have time to go through the details of this. This is again showing some of those numbers that I just mentioned before, but just in terms of the yields, we're going to end up with our prediction is around 260 million galaxy shape measurements for weak lensing, and around 19 million secure redshifts across a range of redshift going out to redshift 3 and beyond. Okay, so how do we do this? Just in terms of the background, obviously this is this new community process that has been developed for the Roman Space Telescope. We had a lot of committee meetings, community white papers that we brought in and analyzed, or there were multiple dozens of those. And then we divided into working groups looking at different aspects of the survey. We also had communications with the community at various community town halls, and I guess this is the next one right now. And then also really important work engaging with the 2 project infrastructure teams for the imaging survey and the spectroscopic survey that led us to a lot of our final architecture. So just, I don't have even close to time to go into all of the inputs from the white papers, but just to point out a lot of the science that folks proposed sort of covers a very broad range, not just the cosmology that is connected to some of the level 1 science requirements, but all the stuff that's listed here, a huge amount having to do with galaxy evolution, gravitational lensing, galaxy clusters, and evolution with redshift, and also some aspects of stellar physics, and as we'll see, even some solar system science. Okay, so these are, again, I don't have time to go through them in detail. This is sort of a just quick grab bag of some of the white paper examples, going from near studies of solar system objects, including trans-Neptunian objects, all the way out to high redshift galaxies and galaxy evolution and clusters and sort of everything in between. And we thought about a lot of these various science goals in terms of thinking about what we could do with our survey. So we had these science goals. We knew we were going to do an imaging survey and a spectroscopy survey. And so the question was, what do the trade spaces look like in terms of how you actually design these areas? And so we started with the cosmological figures of merit, given that those are the level 1 science requirements. And for the imaging survey, it turns out that the figure of merit used for determining the how well you can measure the growth of structure from weak lensing depends primarily on the number of galaxies. So that's the area times the effective density of galaxies on the sky. And it turns out that if you're observing in the H band, is roughly flat with exposure time. If you look along here, so if you chart around 100 seconds per exposure, and then cover either a wider area or a more shallow or a smaller area deeper, you end up with roughly the same number of galaxies that you can get shape measurements of. And so this led us to, there's other considerations in terms of large area and depth, and I mentioned some of those here. And so there are advantages to going wide, and that you have a greater dynamic range for the power spectrum on large scales. There's lots of things you can do, even if you just go with one filter, as we will see, over a wide area. But if you go deeper, that enables higher order statistics with a higher density, gets to higher redshift, and also, this is in a way a distinct capability of Roman or some of these deeper observations. We also realized that we needed to have, at least over a significant part of the survey, we needed to have multiple bands to enable mitigation systematics, and also to get photoses, plus a huge amount of general astrophysics benefits from having multiple bands. And so this again is the recommendation that we came up with that sort of brings all this together. In terms of spectroscopy, one thing that is immediately set for us is that that we need to use the GRISM in order to do the spectroscopy, because we had to have accurate enough redshift for redshift-based clustering. When we had interfaced with the PITs on this and looked at the cosmology of figure of merit, they found that generally, if you go to a larger area and shorter exposures, that will give you the greatest cosmology figure of merit. If we just take that sort of at face value. However, there are some other things that point to this. One is that you need Roman imaging in at least 2 bands in order to decontaminate the spectroscopy. And also you need multiple rolls, but that's we've already baked that in. Also, if you go to greater depth, you get higher signal to noise line detections and go to higher redshift, which is as some of these figures show, is a unique capability of Roman. That adds into both it gives both some margin for the spectroscopic measurements and also adds in a lot of general astrophysics science that one could do. We noticed that we just note that for the deep tier, the aim is to go much deeper, just as it is with the imaging, in order to get calibration of the spectroscopy. And so what we ended up with, at least in terms of our medium tier, was to do that entire medium tier, 2400 square degrees, at this 191 second exposure with 2 exposures and 4 rolls for each one. And that will ultimately yield, as I mentioned, about 19 million galaxy redshifts. Okay, so the last trade space we considered, there were others, the last important one, or big one, had to do with field choice. So where do we put these fields? And some considerations were field of regard of ground-based instruments. We would like to be able to be visible from both the northern and southern hemisphere when possible. Overlap with wide area surveys, and one thing that we really focused on was LSST. The deep multi-band imaging of LSST is really important for maximizing what we can do with the imaging and spectroscopy with Roman. We also thought about solar system science. In particular, if we did some observations near the ecliptic plane, that may allow you to be more likely to pick up interesting small solar system objects. But that if the closer you go to the ecliptic plane, the larger the zodiacal foregrounds are. And also, of course, you don't want to get too close to the galactic plane. And so those things kind of push against each other. One thing, again, as I pointed out before, is the deep tiers. Really, the best tiers for doing that was clear with the LSST deep drilling fields, which have both good multi-wavelength coverage, but also will have very, very deep ground-based imaging. Okay. There were the white papers that we got had a lot of suggestions for things we should do, and there were some of them that we ended up not going towards, but we sort of recognized the benefits of all of these. One is to use the wide filter for doing weak lensing measurements. So we gave a lot of thought to this. It would provide greater depth at a given observing time, but there are real concerns regarding the chromatic PSF bias in such a wide filter. And after a lot of careful consideration, the committee decided that we should not be doing that in certainly in the main core community survey. As I mentioned before, there were a number of surveys that suggested a very wide area. And even the whole sky. And this would maximize galaxy numbers, especially if you're doing something in only a single band. But we need systematics control, and having multiple bands really helps with that. Also, we'd like to get good photoses, etc. And there are other astrophysical applications that demonstrated the value of having 3-band imaging over a large portion of the survey. Likewise, though, we could have just focused on the medium tier and not expanded out into this wider tier. But that would substantially reduce the overall coverage. And as we mentioned, you actually do maximize a weak lensing figure of merit if you have more galaxies. And a large number of white papers advocated for getting as wide as possible. And so you can think of this almost as sort of like a down payment on what could in principle be an even larger wide area survey. And then finally, we had some consideration for doing a additional 2-band tier that would kind of go in between and mitigate some of these concerns. But that would also add additional complexity. We realized that that was really not worth it in terms of the overall benefit. So instead, our H-band imaging is actually the same depth through both the wide and the medium tiers. We have uniform coverage over the whole medium and wide tiers, and that we feel like will be the most useful data set as a legacy product. Okay. In terms of the overguide and the in-guide and underguide, what we decided to do there? So we ended up thinking about the medium tier as sort of a combined core mission survey area. We realized that the area and the depth and the combination of imaging and spectroscopy is really well suited to the area that we have there for the medium tier. So we focused our overguide and underguide allocations onto something quite simple, which is just changing the area of this wideband imaging tier. And really what it comes down to, just where do you do or take away from the observations. And so for the overguide, if we go up by 20 days, we decided to go farther south and cover, it would get us up over 3,000 square degrees for the wide tier, and it would allow us to cover more of some of the fields in the south that are accessible, for example, with the South Pole Telescope, where we'll get excellent deep CMB observations, for example. For the underguide, we wanted to make sure that we continued to have sort of some good coverage in the north and North Galactic Cap and in the South Galactic Cap. And so we decided to reduce both of those roughly equally. And this will, if going with the underguide, this would, just to say, the overguide really gives us quite a lot of additional survey area where it would be really valuable. And whereas the underguide is taking us down once again in terms of the value of this very wide survey that was recommended by a number of white papers, it would reduce the total area to less than 5,000 square degrees and take away some of the access from the Northern Hemisphere. In terms of survey extensions, things that you could do to build on this, a number of white papers suggested doing some imaging in the K-band, which we did not end up putting into the core community survey because it's significantly less sensitive. And so it would have caused us to significantly reduce the area. But this could certainly be added to some part or even all of some of the survey tiers as part of a general astrophysics program. And there's a lot of, in particular, broad astrophysics and galaxy evolution questions that would be really well addressed with the K-band imaging. In terms of going after specific nearby galaxies, there's a lot of benefits to having a smooth contiguous survey field. And so we decided to go for one single field. Some of those nearby galaxies, quite a few, will be covered in the high latitude wide area survey footprint, but we felt that specific galaxies that folks were interested in would make an excellent general astrophysics survey program. There was a lot of galactic science that was proposed, some of which that can be covered by some of the, especially in high latitude, but we could, in principle, do coverage of additional areas of the galaxy or do second passes of some of the areas in order to obtain proper motions. Likewise, we could do additional passes to try to get more solar system objects. One could go wider with the spectroscopy. One could cover, for example, the wide survey tier, especially if it turns out that it's not as important to have multiple band imaging. One could do that, or could go deeper in the spectroscopy and just add on to the multiple observations that we're already doing in the medium and deep tiers. And then in terms of very wide areas, I mentioned a number of people suggested going very wide, and that certainly could be done, either more H-band, or if it turns out that the wide band is actually usable for a number of these cosmology or other applications, one could add on to this survey area with more W-band data. Okay, so that's all I got for you. This, again, just to bring it back to, this is what the survey looks like, and I'd just like to throw it in to look at one of these simulations for what these images will actually look like. It's kind of amazing when you think that we're going to get something like 5,000 square degrees of space-based imaging like this. And so I'll stop there and take any questions. Thank you.
Okay, thanks, Ryan. This is great work. There's a question right away from Adrian Price Whelan.
Sorry, I had to allow WebEx to see my camera. Anyway, this is awesome. Thanks, Ryan, for the overview. I, of course, wish Roman had the guts to do all sky, but I recognize that this would mean relaxing, some of the science requirements on the cosmology side. Anyway, with your current survey proposal, there's an enormous opportunity to enable, legacy future Milky Way science through astrometry, but that would be maximized if the wide survey was done early to maximize baseline. Right. Was there any recommendation on timing of the survey components?
We didn't make I believe at least this point was pointed out in our report. Given the significant timing challenges, in particular for scheduling the other two surveys, we tried to be as relaxed as possible in terms of what our formal recommendations were for doing for the timing of doing this particular survey. I think this is something that is being considered by the ROTAC, and I know that we were actually just talking about this earlier, that the exact plans for how the imaging would get done are sort of being considered as part of the ROTAC process. And so I think there's plenty of space for, in particular, some parts of these surveys, of this survey, to be imaged earlier rather than later. As you can imagine, the overall parameter space for what bits of this you image when is huge. And so I think I don't have a sort of very clear recommendation for you at the moment, but that's certainly something that the ROTAC can come back to and look at. I know that there have been some suggestions, including in white papers, of specifically what we could do.
Cool. Thanks.
Okay, we have about 5 minutes until next next speakers up. So we've got plenty of time for questions.
If I could just build on that, sorry, that point. One other thing is that galactic proper motions are one of just several suggestions for how to optimize the baseline. So as I think I mentioned as well, there are potential reasons for doing particular cadence of observations near the ecliptic plane, for example, because then one is able to potentially identify solar system objects. So there's sort of a number of different possibilities for what the ROTAC could do to optimize that timing. I think I saw a question on the chat, but then it just disappeared.
Oh, I see it. There's a question from Christina Lindberg that says, any idea of what nearby galaxies less than 1 megaparsec are included in the survey footprint?
That's a great question. I don't think we got the actual catalog of those. Yeah, that would be straightforward to do, though. Certainly the area is large enough that it would be a significant fraction of them, of the ones that are at high galactic latitude. I don't know which ones are in particular. This particular footprint, which is both, mostly at high galactic latitude and also at high ecliptic latitude. But that would be a really good resource to have, and I think that's a suggestion I think we could put into to suggest to the ROTAC that once this footprint polygon, yes, we don't think that is on the website, but that's certainly something that we can provide. And just to say that this is a very broad footprint. Again, the area here is really big, and so in consultation with the science operations team, there is certainly going to be some tweaking of the exact shape of this. The main thing is that we hit the key survey fields that we're interested in, and the deep calibration fields.
Yeah, and just to reinforce, these are the recommendations from the committees, and they haven't been assessed for feasibility yet, and so there's still significant work to do. First question up was Jesse Han.
Hey, yeah, thanks for the great presentation. So you mentioned that there's the possibility to pivot to or add a W-band survey if the systematic proves to be, better than suspected. So is there actually room for that kind of maneuver after the first 2 years of observations?
So that, I think, is something that we discussed in the report. There's a discussion of sort of various kind of considerations that one should be thinking about as the first set of observations come through. And so that's certainly, there would be potentially a possibility of doing that. I think one of the things we did say, in terms of the timing of the various pieces of the survey, one important piece is that the calibrations fields get done very early on, so that we had that information about what the actual performance of the both the imaging and the spectroscopy is in terms of what we need to do the various science goals, in particular the cosmology. And so so that's something that I think could, in principle, be a possibility. I think the concern was that for doing the cosmology, that the analysis techniques that we would need to have really good confidence in our ability to do the weak lensing with the W band would need to be sort of developed in parallel with doing a set of observations. And so my understanding from the committee is we didn't have a huge amount of confidence that we could rely on that. But if that capability is there at the time that the deep field observations are being done, then that's certainly something that the project could consider.
Thanks very much.
Sure. Question from Dave Bennett.
Yeah, just a comment. There was an earlier suggestion about maybe doing some of the galactic plane with their survey, but there's a separate galactic plane survey that's been selected. And I think there's like a similar process for, for defining what to do with that galactic plane survey, right?
Right. I think the thought was that, in particular, looking at proper motions of stars in the above the galactic plane at high latitude. I think if I'm interpreting Adrian's question correctly, that would be what you would do here, because
You
it's
do all
exactly
sky,
right.
you don't have to
Hello?
differentiate. I'm
That's
just kidding.
right. Well, you're right that we are deliberately excluding the galactic plane in the survey footprint here, because the extragalactic science is significantly compromised with galactic foreground.
Okay, and I think we'll do our last question, Dominic Bowman's.
Yeah, are there any plans for optimizing the data reduction as a parallel aspect for looking for low surface brightness structures instead of the sensitivity for the point sources?
That was sort of, I think, above our pay grade or outside of our purview, in the sense that we are not making recommendations about what the data analysis procedure would be, but I'm certain there are tons of good applications. I see Julie has her hand up.
Yeah, I just wanted to comment that in the last proposal call, we selected a team to develop a low surface brightness pipeline. It's led by Alex Borloff. So there is work on developing that kind of pipeline. I see Jeff also had his hands up. He may be adding to it.
I was just going to make the same comment.
Thank you.
All right, I think to keep on schedule and keep us not going after 5:30, we better leave it there. But thanks, Ryan, and thanks again to the whole committee for that fantastic report. And so our final speaker for today, representing the High Latitude Time Domain Survey, is Brad Senko.
All right. Hello, everyone. Can you see my slides in full screen yet?
They appeared and they've just disappeared.
They're loading. Ah, there we go.
There you go.
Now I
Yep.
can see them. Can you see them?
Yep, looks good.
All right, excellent. On behalf of myself, Masao Sako, and the entire High Latitude Time Domain Survey Definition Committee, we're very happy to be here and to report to you all, the community, the main stakeholders here, what we recommended for the implementation of the High Latitude Time Domain Survey. These are the folks who are involved in the committee. It was a really enjoyable group to work with. I've not only learned a lot about Roman, but I learned a lot about science that I don't think a lot about on a day-to-day basis. So despite being a lot of hard work, I have really enjoyed going through this process, and I encourage all of you who are going to benefit from Roman to thank the folks who did this, because it was a lot of effort and it was designed to benefit all of you. So it really was, a community service effort. And they did, I think, a fantastic job on this and made Masao and my job pretty easy. So you've seen this plot a couple of times again, but just to remind you all, you heard about the Galactic Time Domain Bulge Survey. You heard about the High Latitude Wide Area Survey. What I want to talk about now is the other of the three main core community surveys, the High Latitude Time Domain Survey. And just so you know, this was an image that was made actually before we made our recommendation. So if you pay careful attention, you'll see that the actual implementation of the High Latitude Time Domain Survey that we recommend is going to look a little bit different than what you can see on this figure here. So the goal driving, the science goal that was driving the requirements for the High Latitude Time Domain Survey is using Type 1a supernova to constrain the cosmology of our universe. Because their light curves are very standardizable, if you measure their peak luminosity and their time scale of evolution, you can infer the distance to these sources quite precisely. And with a distance and a redshift, you can construct a Hubble diagram. You can see a couple of examples of state-of-the-art ones here from the Dark Energy Survey. and from other analysis combining a bunch of different, mostly ground-based facilities. These provided the first evidence for dark energy for the accelerating expansion history of the universe. And by probing them out to higher redshift and with increased precision, we think we can make dramatic improvements on constraints on fundamental cosmological parameters, particularly those surrounding the equation of state, W0, WA. You can see kind of here on the right, where we think we can be with Roman compared to where we are with ground-based surveys. But of course, Type 1a supernova, while they drive a lot of the requirements that we had to meet in designing an implementation for the high latitude time domain survey, what we found was that there were actually a relatively broad range of survey designs that could meet those requirements. And so we spent a good amount of time thinking about how can we optimize over a much broader range of community science to enable the full breadth of this survey to answer lots of different science questions, not just the 1a supernova cosmology. And so to inform us, because none of us on the committee were experts in all the kind of science that people in the community wants to do with the high latitude time domain survey, we went through the same process that all the other committees did that Ryan and Dan told you about earlier. We went through all these fantastic white paper pitches, white paper updates that you all provided. We held a number of workshops in the community forum updates. There's a working group within the Roman project that we've been working, reasonably closely with. And the word cloud here again is just to show you, dark energy supernova. That's only kind of part of the science that this powerful survey will enable. And we really tried hard to think about, having a dual mandate for meeting the cosmology requirements and enabling the full breadth of science that the community wanted in the survey. So to do our work, we split up into 5 working groups. The first was looking at sort of the nuts and bolts of the survey design, the cadence, the filters, the depth, the area. The second was looking at spectroscopy with its onboard prism. Doing spectroscopy is a relatively unique thing that Roman can do, particularly in the near infrared. So we tried to understand the benefits of allocating time to that versus doing more area in the imaging. We spent a good amount of time looking at field selection, where we actually wanted to place the fields. We looked at survey extensions. We'll talk about this more at the end, but you have to build up reference imaging if you're going to do a time domain survey. We wanted to think about, other filters, other time scales, again, to enable this much broader range of science. And then we really tried hard to think about, placing Roman in context of all the other things that are going to be out there. In particular, this contribution of 100 nights of Subaru time to the Roman project, and what that could enable and how that would make you, kind of design the high latitude time domain survey differently if you knew you could have complementary Subaru data and also, complementary Rubin data products to complement the Roman data set. We relied heavily on simulations, and this is where we really leaned on the Supernova project infrastructure team in particular, and they were fantastic and turned around our unreasonable demands extremely efficiently. But we also used our collective knowledge of, the time domain, transient, galaxy, static galaxy science worlds to try to make an informed decisions about the sort of globally optimized survey design. The cadence, filter, depths, area discussions, conversations. We wanted the biggest thing that, the conclusion that was really unanimous amongst the committee was that we wanted to target supernova, to target redshifts, to target bandpasses that were unique to Roman. Rubin, if any of you are at the town hall at AAS, is quite exciting. It's going to be starting up pretty soon. It's going to be finding a large number of Type 1a supernovae at what I'd call intermediate redshifts, around a half. What Roman can really contribute, of course, is at higher redshifts at near infrared wavelengths. And if you look on this plot here, showing, kind of state of the art, right, there's relatively few type 1a supernova that have been found at redshifts greater than 1. These have lots of cosmological power in what they can constrain for the basic parameters describing the expansion history of our universe. And it really can only be done by a wide field near infrared facility like Roman. And so our survey design was really driven to target redshifts that are unique to Roman. That also went into the filters that we want to use. If you want to sample, rest frame optical band passes, if you're looking at redshift 1, redshift 2, that tells you what filters you need to use, and that's what this figure here on the bottom is showing. It determines the depth that you want to reach, because we know roughly how bright type 1a supernova are. If you identify what redshift range you want to detect them in, that tells you, how deep you want to go. The one thing that we had a little bit of leeway on was the cadence for the observations. In particular, at high redshift, the type 1a supernova evolved relatively slowly. And what we tried to do was pick a cadence that was fast enough to capture some of the more exciting, fast evolving transients that people in the community were interested in, shorter time scale supernova, potentially even some of the more distant kilonova that were out there, but that also were not oversampling the type 1a supernova light curves and driving down the figure of merit too much. And then the area is going to be set, largely by the amount of observing time that we have. But it's important to note that not all small areas are feasible. Oh yeah, this is showing, here on the left, where Rubin is really focusing in on redshifts less than 0.7 or so. And, we really wanted to prioritize, again, the higher redshifts with Roman to complement that. Prism spectroscopy. This was, a really unique opportunity that, again, you kind of can't necessarily do from the ground. This was nicely illustrated by this figure from a white paper we got from Greg Aldering, where you can see here the signal to noise ratio for a source with 24 magnitude and an hour exposure from a ground-based 10-meter telescope with, just natural seeing compared to what you can get with the Roman prism. If you're looking out here, past 1 micron, so from 1 to 2 microns, even with a 10-meter telescope, Roman is going to be more powerful. And so we view that as something, again, that was quite unique and powerful that Roman could do on the one hand. On the other hand, it's quite expensive, right? You're dispersing the light. If you want reasonable signal to noise ratios, even if you're summing them over, multiple different epochs, it takes a lot of time. And so we looked pretty carefully at how the various metrics for the type 1a supernova varied as a function of how much time we spent doing prism spectroscopy. What we found was that in general, prism fractions on order 10, 20, 30% yielded reasonably similar performance for the type 1a supernova figures of merit. Pushing down to 0, we didn't want to do because, again, we thought this was unique. Also could have some cosmological application if you use things like twinning techniques and, relatively unique community science spectra for training machine learning classifiers. So we tried to dial in, ratios that were in, the 10, 20, 30% range and look at what those might look like. For the field selection specifically, we have a requirement that we need to be in the continuous viewing zones. We want light curves that are continuous over a 2-year phase. And the only way to get that for a facility like Roman is to be sitting in the continuous viewing zones. What that meant was that we had to look at either high ecliptic latitudes above plus 54 or low ecliptic latitudes below minus 54, sort of mid-ecliptic latitudes, where, as you just saw, a lot of the high latitude wide area survey was positioned where some of the best studied multi-wavelength fields like the Cosmos field and the Chandra Deep Field South, unfortunately, those are ruled out for us. On the positive side, they have very low zodiacal background. It's relatively straightforward to find areas that have low galactic extinction. And so what we ended up recommending was that we position some of the area for the high latitude time domain survey in the south, specifically around the Euclid Deep Field South, and some of it in the north, specifically around the Elias N1 field. And I'll show you an image at the end of what that kind of looks like in its detailed implementation. But we thought that splitting it up into two areas, while you do pay a price for slewing the telescope, would be extremely useful for a number of reasons. One, because there's always going to be some area of the high latitude time domain survey that will be visible from the ground. Two, because you can remove any concerns about cosmic variance by only looking at one area of the sky. And three, because you can make use of both Rubin and Subaru to provide really nice complementary data sets. Whereas if you're only looking in the south, you could only use Rubin. If you're only looking in the north, you could only use Subaru. Okay, so one of the big assumptions that we made when we were putting together our survey design surrounds the complementary data. What we found is that the figure of merit calculation depends very sensitively on having a good low redshift sample to anchor the Hubble diagram. And if you don't assume that you're going to include an intermediate sample from Rubin at a redshift of 6, you're going to get a very different looking survey than the one that we implemented. You're going to get a survey that covers a very large area, 100 square degrees or more, and does a lot of it in filters, optical filters, R band and I band, things that you could, and Rubin will, do from the ground. We strongly prefer not doing that. Strongly prefer doing things that Roman can uniquely do. And so we, pushed on the design in that way. However, it's important to note that while, Rubin data will be broadly available to the US community, it may not necessarily be available to the entire worldwide community and hence the entire Roman community. And so we have encouraged the project, and they are in the process of doing this, of trying to make some data sets available, in particular supernova 1A light curves from the Euclid Deep Field South from one of these nice LSST deep drilling fields, so that people who want to do cosmology with Roman, they have the intermediate redshift sample, they have the Roman sample, they can go out and do all of that science. I mentioned before Subaru time. We thought a lot about, how best to use this. Some of our team members went to the workshop that was in December in Japan, and we're sort of in the process of working through some of this. But for the high latitude time domain survey, you could imagine lots of great usages: host galaxy spectroscopy, after transients fade away, or even before, transient classification, characterization, even concurrent imaging with the Hyper Supreme Cam. And so, we're kind of in the process of defining the scope and trying to see, how many of these nights we could get to use, because we think it would be very powerful. And if there is no, for example, possibility of using Subaru time, that might have caused us to revisit this question of splitting the fields up into the north and the south. Okay. So last couple of slides, the details of the implementation. What is this going to look like? For our in-guide recommendation, which was 180 days, the sort of nominal survey design that we're recommending to the project, we recommend 3 components. The first is this core survey. In the middle 2 years of the 5-year Roman mission lifetime. This is revisiting the same fields every 5 to 10 days, some in the north, some in the south, And this is where the bulk of the supernova and other transient discoveries are going to come from. And that's the main and what we'll use the largest fraction of the time that we're recommending. At the same time, we were concerned that waiting a full year and a half before beginning any observations for the high latitude time domain survey was very risky. It's risky because you're not going to have reference imaging for the fields that you want to observe. And so it's hard to know, whether sources that you're discovering are new initially. It's risky because there are a lot of assumptions that went into our analysis. We don't know what the rate of supernova 1A at redshift 1.5 is very precisely. We don't know exactly how the instrument is going to perform. And so what we recommended was a small pilot survey, 7 or 8 epochs of the area that we're going to cover during the main survey, but over the course of the first few months, so that we can build reference images, test pipelines, discover enough high redshift type 1A supernova to know, are we actually going to find enough to meet the figure of merit requirements? And if we do that in the first 5 or 6 months, we should know, then we can, easily, make adjustments to the core survey if we need to. The other component that we recommended was a temporally extended component. The great thing about, Roman looking in the near infrared, it's great for high redshift sources. Sources that are high redshift naturally have higher timescales. Some of the more interesting sources we got, really compelling white papers about pair instability supernova from the very early universe, superluminous supernova, tidal disruption events. These all have timescales intrinsically in their rest frame that are order of 6 months, maybe a year. When you fold that into seeing them at, redshift 3, 4, 5, benefiting from the entire 5-year duration would be very powerful. And so we recommended a small number of extended epochs of the deep fields, looking with the, more near infrared filters that could, double or triple the sample of, well-characterized slow time scale transients. Here's a bit more, numerical detail for the core component. Again, the largest fraction of time, 158 of these 180 days. 2 tiers, a wide and a deep tier. The wide tier targeting type 1As at redshift 0.9, the deep tier targeting type 1As at redshift 1.7. We recommended a 10-day interlaced cadence for the imaging part of this survey. What we mean by interlaced is we revisit a subset of the filters in day 1, another subset of the filters 5 days later, and come back to that other subset after 10 days. So you're only getting the full set of filters every 10 days, but you are returning to the same fields every 5 days. And so that provides you with a nice handle on some of the faster timescale transients. We only recommended some of the bluer filters for the wide survey, redder filters for the deeper survey, again, to, sort of match the redshift of the type 1A supernova we're looking at. The pilot component, 15 days total, early science, templates, preparation, 8 visits to all the imaging and prism fields in the first 5 months. And then, a pretty small extended component for long-term monitoring for high redshift and exotic transients. Okay, what the fields actually could look like. I think there's something that's going to zoom in here. Yeah, so on the left, the Elias North 1 field. On the right, on the Euclid Deep Field South, showing the sort of 2 Rubin pointings that are going to be done. You can see sort of the wide and deep tier sort of wedding cake strategy here. And the wide and deep tier covering the different pointings here that Rubin is going to do specifically so that we can have this really nice overlap. Sort of the actual areas this works out to be, 15 square degrees for the wide, 6 square degrees for the deep imaging, 4 square degrees for the wide, and about 0.6 square degrees for the deep prism. For our under and over guide requests, the under guide was hard, 160 days. It's a pretty significant reduction. We recommended eliminating the extended component entirely. While this was really powerful for broader science, it wasn't strictly necessary to meet the Supernova 1A cosmology goals. But that wasn't enough. We also needed to reduce the wide imaging area slightly in order to fit within that. Obviously, we didn't think that was ideal. For the overguide, we tried to enable even more broad community science. We recommended deep K-band observations over the 5-year Roman mission lifetime. This wasn't a part of our in-guide recommendation for a couple of reasons. One, because it's a lot less sensitive and so required a lot of time. Two, because the Supernova 1A folks considered it to be pretty useless because the K-band calibration requirements are significantly relaxed. And we also recommended deep R-band observations to complete the full set of all of the broadband Roman filters in our fields to enable, more static galaxy science. So with that, I will gladly stop. Thank you all and take any questions.
Thanks very much, Brad, and also the whole committee and everyone who contributed. That's great. We certainly have time for a few questions for Brad and the committee. Question from Ryan Foley.
Hi, Brad. Thanks for all your hard work and for the committee's work. I was just wondering, since the field of regard, we actually won't know what it's going to really be until after launch. If it happens to be better than the current requirement, and we're able to look at CDF South, would you recommend moving a field there?
Yeah, so there's a lot of interest from the Galaxy people in using that as our southern field. We were told by Jeff, and he may want to weigh in on here, that we should not plan on that. But if that was possible, I think there would have been a lot of interest in the committee for using Chandra Deep Field South for the southern field.
I think it would make sense here to invite Jeff to comment on why there is not the flexibility you think there might be.
So I think what I told Brad was don't plan on it. And when I've talked to the engineering team here, that is what they have told me as well. But of course, Ryan's right. We won't really know what the field of regard is until after launch. And if we find it is bigger than we expect now, then we would certainly allow people to consider using it. So I'm not quite sure what guidance to give other than, I wouldn't put a huge amount of effort into planning on it because right now I have zero assurance we could do that. But, we're not going to be stupid. If we find we can, we will allow people to do it. And then after that, it's beyond what advice I would give as to how to go about that.
Okay, thanks.
We're not going to know this until after we've accepted a bunch of analysis proposals that may well be banking on the field being where we put it. So the threshold to make such a substantial change might actually be quite high.
Yeah, that's fair.
So it sounds like it's something that certainly would be considered for a later round of General Astrophysics Survey proposals as well. We have time for more questions for Brad. I don't see any in the chat, and I don't see any hands up. So going once, twice. All right, nothing there. Okay, well, I just want to say thanks to Brad, and thanks for the other two people presenting, and also for the tremendous amount of work from these committees. We're I don't know if we're quite on the home straight yet, but we've certainly made major milestones towards knowing what a large fraction of the entire Roman mission is going to look like. We now look forward to the work of the ROTAC, who the list of committee members was in the invite email. It will be online shortly, and so that there'll continue to be future presentations this year from when we get some progress on the ROTAC and where that's going. So we'll announce that through similar events like this. But for now, thanks for everyone for joining, and thanks for presenting, and go Roman.